Right now, 250 miles above your head, astronauts orbit Earth inside a pressurized metal shell. If something goes catastrophically wrong, a rescue spacecraft can bring them home in hours. Move to the moon, and rescue takes days. Move to Mars, and a distress call takes 22 minutes, just to reach the people who could help. No one is coming in time. Move to Jupiter, and the delay stretches past 40 minutes each way. Move to the edge of the solar system, and a single message home takes over 20 hours to arrive. Move beyond that, toward the nearest star, and help is not delayed. It is gone. Space does not get more terrifying because the universe gets worse. It gets more terrifying because Earth gets further away. If you enjoy these explorations into deep space, take a moment to like and subscribe. It keeps this channel going and means more than you know. Now, are you comfortable? Let's begin. The International Space Station circles the planet once every 90 minutes. It moves at roughly 17,500 miles per hour, fast enough to cross the continental United States in about 10 minutes. From the inside, you do not feel the speed. You feel the silence, the hum of air recyclers, the faint vibration of fans pushing atmosphere through narrow corridors lined with cables and equipment racks. Outside the windows, Earth fills half the sky, close enough that astronauts can identify individual cities at night by the pattern of their street lights. Close enough that they can watch storms form in real time across entire ocean basins. Close enough that if something goes catastrophically wrong, they can be home in hours. That closeness is the single most important fact about life on the station. Not the technology, not the training, not the billions of dollars of engineering wrapped around every system on board. The reason people survive in orbit is that Earth is right there. The station floats at an altitude of roughly 250 miles. In cosmic terms, that is nowhere. It is roughly the driving distance between New York and Washington, D.C., except the road goes straight up. You could stack that distance end to end with commercial airline flights and cover it in under an hour. The station is so close to the planet that its orbit actually decays from the faint drag of the uppermost atmosphere. Without periodic boosts from visiting spacecraft, it would slowly spiral downward and re-enter. The astronauts aboard it live in space, technically, but they live on the porch. The front door is right behind them, and it is always unlocked. The space on the other side of the hull, however, is already trying to kill them. The vacuum outside the station walls would cause a human being to lose consciousness in roughly 15 seconds and die within 1 to 2 minutes. Temperatures on the sunlit side of the station reach approximately 250 degrees Fahrenheit. On the shadow side, they plunge to roughly minus 250 degrees Fahrenheit. The station crosses from full daylight into complete darkness and back again every 45 minutes. Micrometeorites, tiny fragments of natural debris and human-made junk traveling at thousands of miles per hour, strike the exterior on a regular basis. The shielding is designed to absorb impacts from particles up to about a centimeter across. Anything larger could puncture the hull. Inside, a quiet war is fought every second against the physics of the void. Air pressure must be maintained within a narrow band. Oxygen must be generated continuously, either chemically or through electrolysis of water. Carbon dioxide must be scrubbed from the atmosphere or it accumulates to dangerous concentrations within hours. The water recycling system processes urine, sweat, and humidity from exhaled breath back into drinkable water. Every calorie the crew consumes was launched from Earth on a cargo vehicle at a cost of roughly $10,000 per pound of payload. If the carbon dioxide scrubbers fail, the crew has a limited window to fix them before cognitive impairment begins. If the oxygen generation system goes down, backup supplies are finite. This sounds terrifying, and it is. But here is the detail that separates the station from everything deeper in space. When something goes wrong 250 miles above the planet, help is minutes away in communication terms and hours away in physical terms. A crew member can press a button and speak to mission control in Houston, and the response arrives within seconds. Flight surgeons monitor crew health data in near real time. If a fire breaks out, ground controllers can see telemetry from the affected module almost instantly and advise. If a toxic ammonia leak contaminates a section of the station, the crew seals hatches and retreats to a safe module while engineers on the ground analyze sensor readings and plan the response. If the situation becomes truly unrecoverable, a docked spacecraft, either a SpaceX Dragon or a Russian Soyuz, is always available as a lifeboat. The crew boards, undocks, and re-enters the atmosphere. From the moment they close the hatch to the moment they are floating under the parachute above the ocean or the step, a handful of hours pass. That is the safety net. It is real, it is robust, and every thread of it depends on one thing. The station is close to Earth. Think about what that safety net actually consists of, because each thread will snap at a different distance, and understanding which ones go first is essential to understanding why space gets more frightening with every mile. The first thread is voice. On the station, communication with the ground operates in near real time. The signal bounces through a constellation of relay satellites in high orbit and reaches Houston in a fraction of a second. A crew member experiencing a medical emergency can describe symptoms, while a flight surgeon listens, asks questions, and gives instructions as if they were in the same room. This is not a convenience. It is a survival tool. The ability to talk to an expert in real time has prevented emergencies from becoming fatalities more than once in the station's history. The second thread is rapid return. A docked spacecraft means the crew always has an escape route. The return trip from the station to Earth's surface takes somewhere between 6 and 24 hours, depending on the vehicle and the landing profile. If a crew member suffers a medical event that exceeds the station's limited treatment capability, a stroke, a severe allergic reaction, an injury that requires surgery, the option exists to bring them home to a hospital within a day. That option does not exist anywhere else humans have ever traveled, except the station and the short-duration moon missions of the Apollo era. The third thread is resupply. Cargo vehicles visit the station multiple times per year. They bring food, water, clothing, scientific equipment, spare parts, and personal items. If a critical pump fails, a replacement can be manifested on the next cargo flight. If a new medical need arises, medication could be sent. The station is not self-sufficient. It never has been. It survives because Earth keeps feeding it. The fourth thread is expertise. The ground team supporting the station includes thousands of engineers, scientists, physicians, and technicians. Every system on the station has a dedicated team on the ground that monitors its performance, predicts failures, and plans maintenance. The crew is highly trained, but they are generalists. The deep specialists sit in offices in Houston, in Munich, in Moscow, in Tsukuba. When something breaks in a way that nobody on board fully understands, the people who designed it are a phone call away. These four threads, voice, return, resupply, and expertise form the invisible infrastructure of survival in orbit. Astronauts do not think about them the way you do not think about the air in your lungs. They are simply there, woven into every procedure, every checklist, every training scenario. But they are there because of proximity. Every single one of them weakens with distance. In January 2026, the station experienced something that had never happened in its 25 years of continuous human occupation. A crew member became seriously ill. NASA did not publicly identify which member of the 4-person crew 11 was affected, and the agency did not disclose the nature of the medical condition. What NASA did announce was that the situation was serious enough to cancel a planned spacewalk, recall the crew from normal duties, and begin preparing an early return to Earth. The decision moved fast. On January 7th, NASA postponed the spacewalk and acknowledged the medical concern. On January 8th, the agency announced that all 4 members of Crew 11 would return early. By January 14th, the crew had boarded their SpaceX Dragon capsule, undocked from the station, and begun the journey home. They splashed down in the Pacific Ocean off the coast of California at 3:41 in the morning on January 15th. From the first sign of the medical problem to the moment the crew was back on Earth, roughly 1 week passed. During that week, Mission Control managed the situation in real time. Doctors consulted with the crew directly. The return trajectory was calculated and verified. Recovery teams were positioned. The capsule was checked and cleared. The whole operation unfolded the way it was designed to. Not perfectly, not without stress, but with every thread of the safety net bearing weight exactly as intended. The medical evacuation proved that the safety net works when the emergency is acute and identifiable. But there is another kind of emergency on the station, one that is slower, harder to fix, and far more unsettling in its implications. It does not arrive as a sudden alarm. It arrives as a number that changes by a fraction each week, a slow bleed that no single repair has been able to stop. Since 2019, hairline cracks in the transfer tunnel of the station's Russian service module have been leaking atmosphere into space. The affected section, a small vestibule connecting the module to a rear docking port, began losing air at a rate of roughly 1 pound per day. Over the following years, Russian crews applied sealants, hunted for crack sources using dust accumulation tests, and periodically isolated the tunnel from the rest of the station. The leak slowed at times. It returned at others. By 2024, the rate had roughly doubled to between 2 and 2.5 pounds of air per day, and NASA elevated the issue to the highest level of risk on its safety tracking system. The chair of the ISS Advisory Committee stated publicly that NASA had expressed concerns about the structural integrity of the tunnel and the possibility of a catastrophic failure. Russian engineers disagreed, maintaining that a catastrophic breach was not realistic. The two agencies could not reach consensus on the root cause or the appropriate fix. In early 2026, the leak appeared to stop. For a brief period, pressure measurements stabilized. Then, in late May, the leak returned and the rate accelerated. On June 5th, 2026, NASA ordered 5 astronauts aboard the station to shelter inside a docked SpaceX Dragon capsule, prepared if necessary to undock and evacuate the station entirely. 2 Russian cosmonauts remained in the Russian segment, attempting a structural repair on the cracked tunnel while their colleagues waited inside a vehicle that could undock and re-enter the atmosphere within hours. The repair was paused, New measurements needed to be assessed. Roughly 2 hours after the shelter order, NASA cleared the crew to return to normal operations. No one evacuated. But for those 2 hours, the crew of the International Space Station sat inside a lifeboat, suited up, while engineers on 2 continents debated whether the structure around them was sound. This is a different kind of emergency from the January medical evacuation. The medical event was sudden, individual, and resolvable by bringing one person home. The air leak is structural, collective, and ongoing. It has persisted for over 6 years. It has defied multiple repair attempts. And it is a reminder that even 250 miles from Earth, where every thread of the safety net is at its strongest, the station itself is aging. Metal fatigues, seals degrade, cracks propagate along stress lines that were never anticipated when the module was launched more than 2 decades ago. The station survives this because it is close to Earth. Replacement air can be launched on cargo vehicles. The crack section can be isolated while the rest of the station remains habitable. The crew can shelter in a capsule that reaches the ground in hours. The leak is dangerous, but managed because every tool available for managing it depends on proximity to the planet below. Now hold that picture in your mind. A medical emergency on the station. Decision to return. Return executed. Crew on the ground within days. That is what rescue looks like 250 miles from Earth. That is the standard against which every other distance in this story will be measured. And the first place where that standard begins to stretch is the moon. The moon sits at an average distance of roughly 239,000 miles from Earth. That is nearly 1,000 times farther than the station. The communication delay at lunar distance is approximately 1.3 seconds each way, roughly 2.6 seconds for a round trip. That sounds small. It is small enough to hold a conversation, though with an awkward rhythm, a half-beat pause between every statement and every response, like talking to someone on a bad phone connection. It is tolerable, but it introduces something that does not exist on the station. A gap. A moment between the question and the answer where you are alone with the problem. At lunar distance, a docked spacecraft cannot bring you home in hours. The journey from the moon back to Earth takes roughly 3 days. If a crew member experiences the same kind of medical event that prompted the January 2026 evacuation, the return clock does not start at 6 hours. It starts at 72. 3 full days inside a capsule with limited medical equipment, limited medication, limited diagnostic tools, and a sick or injured crew member whose condition may be deteriorating. Resupply at lunar distance does not exist in any meaningful sense. No cargo vehicle can be launched and delivered to a crew on or near the moon within a useful time frame during an emergency. Whatever supplies you brought, those are the supplies you have. If a critical component breaks and you did not bring a spare, there is no next shipment. The expertise thread still holds. Conversations with the ground are possible and close enough to real time that surgeons can guide procedures and engineers can walk through troubleshooting steps. The gap is small, an annoyance rather than a barrier, but the gap is there. And every mile past the moon makes it wider. The most famous demonstration of what a crisis looks like at lunar distance happened on April 13th, 1970, aboard a spacecraft called Apollo 13. The mission was supposed to be the 3rd crewed landing on the moon. It became the most dramatic rescue in the history of spaceflight, and it revealed exactly how thin the margin of survival becomes when you move away from Earth. 56 hours into the flight, at a distance of more than 200,000 miles from Earth, an oxygen tank in the service module exploded. The blast ruptured a second tank and crippled the spacecraft's power and life support systems. Within minutes, the command module, Odyssey, was dying. Its oxygen was venting into space. Its fuel cells were failing. Its electrical system was shutting down. Commander Jim Lovell looked out the window and saw a cloud of gas streaming from the side of the spacecraft. He reported the situation to Houston with a sentence that became one of the most famous in human history. "Houston, we have had a problem." The problem was not small. The crew had lost the systems they needed to survive the trip home. The command module could no longer sustain them. The lunar module, Aquarius, designed to support 2 people on the surface of the moon for a day and a half, became their lifeboat. 3 astronauts crammed into a vehicle built for 2, rationing power, rationing water, and watching the temperature drop as they shut down every system they could to conserve electricity for re-entry. Mission Control in Houston worked the problem in near real time. The communication delay was roughly 1.3 seconds each way. Engineers could hear the crew, talk to the crew, and solve problems together in something close to real time. Teams on the ground built improvised carbon dioxide scrubbers using materials the crew had on hand, tested them in Houston, and talked the astronauts through assembly step by step. Flight dynamics officers calculated a new trajectory that used the moon's gravity to slingshot the crippled spacecraft back toward Earth. Physicians monitored crew health through voice reports and telemetry. The return took 4 days. The crew endured freezing conditions. They rationed water to 6 ounces per person per day, roughly 1/5 of normal intake. Condensation covered the walls of the lunar module. Sleep was nearly impossible. But throughout the ordeal, the crew was never truly alone. Houston was there, delayed by a heartbeat, but there. The engineers who designed every component of the spacecraft were sitting in that room. The doctors who had trained for this kind of scenario were sitting in that room. The mathematicians who could plot a trajectory around the moon and back were sitting in that room. When Lovell needed a corrected burn procedure, Houston sent it. When the crew needed to know which circuit breakers to throw in what sequence to bring the dead command module back to life for re-entry, Houston figured it out and read the list. The crew splashed down safely in the Pacific on April 17th. The mission was called a successful failure. It succeeded because rescue, though slow and desperate, was still physically possible. 3 days of communication. 3 days of ground support. 3 days of improvisation, guided by thousands of experts working in the same time zone as the crew. That was the margin. And it held because the moon is close enough for voices to travel in real time. Apollo 13 set a record that stood for 56 years. The crew reached a maximum distance of approximately 249,000 miles from Earth, farther than any human beings had ever traveled. That record stood until April 2026, when NASA's Artemis II mission carried 4 astronauts beyond the moon on a 10-day flyby that reached approximately 252,756 miles from Earth. The crew, Commander Reed Wiseman, pilot Victor Glover, and mission specialists Christina Koch and Jeremy Hansen, traveled farther from the planet than any human beings in history. Artemis II was a test flight. Its purpose was to verify the Orion spacecraft systems on a deep space trajectory, test communication and navigation capabilities, at lunar distance and demonstrate the procedures that future landing missions will require. The mission succeeded, but it also underscored a reality that the Artemis program's future missions will confront directly. At that distance, a catastrophic failure would have left the crew days from home with no space station to shelter in, no backup vehicle waiting in orbit, and no way to accelerate the return. Everything the crew carried with them was everything they had. NASA is working toward a crewed lunar landing as early as 2028, which would be the first since Apollo 17 in 1972, though the timeline has shifted repeatedly and remains uncertain. When that landing happens, astronauts will step onto the surface of the moon and depend on a suit, a lander, and a finite supply of oxygen and power to keep them alive in an environment that offers no atmosphere, no magnetic field, and temperature swings of more than 500 degrees Fahrenheit between sunlight and shadow. If a suit fails, the crew member has minutes. If the lander fails to ascend from the surface, there is no rescue vehicle that can reach them in time. The return to orbit depends entirely on the lander's propulsion system performing correctly. If it does not, no other spacecraft in lunar orbit or on Earth can descend to retrieve them. Every safety thread still holds at lunar distance, but each one is thinner. Voice works, but with a gap. Return works, but it takes days instead of hours. Resupply doesn't exist during the mission. An expertise is available, but filtered through a delay that turns every exchange into a slightly slower, slightly clumsier version of the real-time support the station crew receives. Here is what the moon teaches. 250 miles up, the safety net is strong enough that a medical evacuation can be planned and executed within a week. 239,000 miles away, a catastrophic explosion requires 4 freezing, terrified days of improvisation just to survive the trip home. And the outcome depends on the fact that Houston can still talk to you without meaningful delay. The difference between those two realities is distance, not different dangers, not a more hostile environment, not worse engineering. The same kinds of failures, the same physics, the same fragile human bodies. The only variable that changed was how far away Earth was when things went wrong. And Mars is not a little farther than the moon. Mars is a different world in every sense of the phrase. The minimum distance between the two planets is roughly 34 million miles. The maximum is over 250 million. A signal from Mars does not arrive in a heartbeat. It arrives in minutes, sometimes more than 20. That single fact, the delay, changes everything about what a crisis looks like, what rescue means, and whether the word help still has any meaning at all. Every thread that held during Apollo 13, every voice, every instruction, every improvised solution passed between a crew and the thousands of experts behind them depended on one condition. The conversation was happening in real time. On Mars, that condition does not exist. There is a moment during every conversation when you say something and wait for the other person to respond. Usually that gap lasts a fraction of a second, so short your brain does not register it. You speak, you hear, you speak again. The exchange is seamless because the delay is invisible. Now stretch that gap to 3 minutes. You say something. 3 full minutes of silence pass. Then a voice answers. But the answer is not responding to what you just said. It is responding to what you said 6 minutes ago, because the person on the other end experienced the same 3-minute wait before they heard you. By the time their reply arrives, the situation may have changed. You may have already acted. You may have already failed. Now stretch the gap to 12 minutes. Now to 22. That is communication with Mars, and it changes everything. The distance between Earth and Mars is not fixed. Both planets orbit the Sun, and their relative positions shift constantly. At their closest approach, called opposition, they are separated by roughly 34 million miles. At their most distant alignment, when the Sun sits directly between them, the gap stretches past 250 million miles. The communication delay mirrors this range. At closest approach, a one-way radio signal takes approximately 3 minutes to cross from one planet to the other. At maximum separation, that delay exceeds 22 minutes in one direction. A round trip, question and answer, takes between 6 and 44 minutes, depending on where the planets sit in their orbits. Those numbers sound like a technical detail. They are not. They are the difference between a managed emergency and an unmanageable one. And to understand why, you have to see what delay does to each of the survival threads that kept crews alive at the station and on the way to the moon. Start with voice. On the station, a crew member can report a fire and receive instructions from a flight controller within seconds. The controller sees telemetry, hears the crew, assesses the situation, and responds. The process is fluid. On a mission to Mars, that same fire report would leave the spacecraft traveling at the speed of light, cross millions of miles of vacuum, and arrive at mission control somewhere between 3 and 22 minutes later. The controllers would see it, process it, formulate a response, and transmit that response back. Another 3 to 22 minutes would pass before the crew heard the answer. In the best case, the round trip takes 6 minutes. In the worst case, it takes 44. A fire inside a spacecraft cabin is not a 44-minute problem. It is a 3-minute problem. Toxic fumes from burning insulation can incapacitate a crew member in under 60 seconds. A fire that compromises hull integrity can lead to decompression in minutes. By the time a message from Mars reaches Houston and a response travels back, the fire has either been extinguished by the crew acting on their own, or the crew is dead. There is no middle scenario. The ground cannot help. Not because the engineers are incompetent. Not because the communication system failed. Because light is too slow. And there's a period during every Mars mission when even that slow, delayed communication disappears entirely. It is called solar conjunction. Roughly once every 26 months, Earth and Mars move into positions on opposite sides of the Sun. When this alignment occurs, the Sun sits directly between the two planets, and its corona, the superheated outer atmosphere of churning plasma that extends millions of miles into space, blocks and distorts any radio signal attempting to pass through it. The effect is not subtle. During superior conjunction, the signal does not merely weaken, it becomes unreliable to the point of uselessness. Commands sent through the corona arrive garbled, or do not arrive at all. Telemetry from the spacecraft becomes corrupted. For a window lasting roughly 2 weeks, and in some geometries longer, communication between Earth and Mars is effectively severed. NASA manages this today with robotic missions. Before each conjunction period, engineers upload a full set of pre-planned commands to the rovers and orbiters operating at Mars. The machines execute those commands autonomously for the duration of the blackout. No new instructions are sent. No telemetry is actively monitored. The rovers are typically placed in a safe parking configuration, performing only low-risk science activities that do not require ground oversight. When conjunction ends and the signal path clears, communication resumes, and the ground team reviews what happened during the gap. For a robotic rover, a 2-week communication blackout is manageable. The rover does not get sick, it does not run out of food, it does not experience a fire or a depressurization or a psychological crisis. It waits. A human crew cannot simply wait. 2 weeks without any contact with Earth means 2 weeks without medical consultation, 2 weeks without engineering support, 2 weeks without updated weather data for solar particle events, and 2 weeks without the psychological anchor of hearing another human voice from home. Every emergency that occurs during conjunction must be resolved entirely by the crew, with no possibility of even delayed advice. The gap is not measured in minutes, it is measured in days, and it is not caused by distance alone. It is caused by the geometry of the solar system placing an entire star between the crew and everyone they know. A conjunction blackout would occur at least once during any crewed Mars surface stay, and depending on the mission timeline, the crew might experience it during the most operationally intense phase of the surface mission, when systems are under heaviest use and the probability of hardware failure is highest. The blackout is predictable. It can be planned around, but it cannot be eliminated. The sun does not move aside to accommodate human schedules. And for those 2 weeks, the crew on Mars would experience something no astronaut in history has ever faced. Total communication, silence, not delay. Silence. The transmitter works. The antenna is pointed correctly. The signal leaves the spacecraft and travels toward Earth, and the sun swallows it. This is the fundamental shift that Mars represents. At the Moon, delay is an inconvenience. 2.6 seconds of awkward lag that makes conversations feel slightly off, but does not prevent real-time collaboration. At Mars, delay is a wall. It separates the crew from every expert on Earth in a way that cannot be bridged by better technology or faster computers. The speed of light is a physical law, not an engineering problem. No future invention will make a signal cross 34 million miles in less than 3 minutes. The delay is permanent, and it forces a complete redesign of how missions operate. On the station, mission control makes many decisions for the crew. Flight controllers manage power allocation, plan spacewalks, sequence experiments, and monitor environmental systems. The crew executes, and the ground oversees. On a Mars mission, that relationship inverts. The crew makes the decisions. The ground advises, but the advice arrives minutes or hours after the decision was needed. This is not a subtle change. It is a structural transformation of how human spaceflight works. For 60 years, the model has been crew and ground working as a single unit, separated by geography but united by real-time communication. Mars breaks that unit apart. Now consider medicine. On the station, NASA's flight surgeons monitor astronaut health through daily private medical conferences, telemetry from wearable sensors, and scheduled examinations. If a crew member reports chest pain, a flight surgeon can ask follow-up questions, review heart rate data, and guide a diagnostic procedure in real time. If the situation escalates, the decision to evacuate can be made within hours, and the crew member can be in a hospital within a day. On Mars, a crew member reporting chest pain would transmit the report. 12 minutes later, a flight surgeon would receive it. The surgeon would review whatever telemetry had been included, formulate questions, and transmit them back. 12 minutes later, The crew would receive those questions. They would answer. 12 minutes later, the surgeon would hear the answers. By this point, more than 36 minutes have passed since the initial report, and the surgeon still does not have a diagnosis. The back and forth that a doctor in an emergency room would complete in 90 seconds takes the better part of an hour on Mars, and that hour assumes the planets are at average distance. Near maximum separation, the same exchange would take over 2 hours. Now place that delay over a cardiac arrest. The standard protocol for cardiac arrest is to begin CPR within seconds and deliver a defibrillator shock within minutes. On the station, a flight surgeon can talk a crew member through this procedure in real time. On Mars, the crew member performing chest compressions would be working from memory and training alone. There would be no voice on the other end adjusting the cadence, no specialist interpreting the heart rhythm, no real-time guidance of any kind. The delay does not merely slow help, it eliminates it. Whatever the crew knows how to do at the moment the emergency begins is the sum total of available medical expertise. Nothing more is coming in time. NASA has studied this problem extensively. The agency identifies behavioral health, radiation, and distance from Earth as 3 of the primary risks for deep space human missions. Research into autonomous medical systems, artificial intelligence-assisted diagnostics, and expanded crew medical training is ongoing. But the honest assessment from the agency's own documentation is blunt. A deep space mission cannot be aborted in order to return an injured crew member to Earth the way the station can. The crew must be capable of handling medical emergencies independently, and the range of emergencies they might face over a multi-year mission is wide enough that no training program can cover every scenario. The pharmaceutical problem compounds this. Medications degrade over time, and research published by NASA scientists shows that drugs stored aboard the International Space Station for extended periods experience measurable loss of active ingredients. A study examining 36 drug products with long-duration exposure to the space environment found that medications stored for up to 2.4 years in low Earth orbit showed increased rates of degradation compared to identical products stored on the ground. The space radiation environment, particularly the higher energy particles found beyond Earth's magnetic shielding, accelerates chemical breakdown in certain compounds. A Mars mission lasting 2 to 3 years would push the medication supply past the tested limits of pharmaceutical stability. The crew might reach the point of a medical emergency and discover that the drug they need has lost enough potency to be unreliable. Return windows impose another dimension of danger that has no parallel in station or lunar operations. The station crew can evacuate at any time. Apollo crews could abort and return within days. A Mars crew cannot simply turn around. The physics of orbital mechanics dictate when a transit between the 2 planets is possible. Launch windows for the return trip from Mars to Earth open approximately once every 26 months. If a crew arrives on Mars and a critical failure occurs during the first weeks on the surface, they may face a wait of more than 2 years before the planets align for a return trajectory. During that wait, they must survive on whatever supplies they carried, whatever resources they can extract from the Martian environment, and whatever repairs they can improvise with the tools and materials on hand. This is not speculation. It is the architecture of every serious Mars mission design that NASA and other agencies have studied. The total mission duration for a crewed round trip to Mars, including transit time in both directions and the surface stay, is estimated at approximately 2 to 3 years. The crew will spend roughly 6 to 9 months traveling to Mars, between 12 and 18 months on the surface waiting for the return window, and another 6 to 9 months traveling home. For the entire duration, resupply from Earth is effectively impossible. Cargo vehicles take just as long to travel to Mars as crewed vehicles do. There is no express lane. A broken water recycler on the station gets replaced by a part from the next cargo flight. A broken water recycler on Mars gets fixed by the crew, or it does not get fixed at all. Consider what the return window constraint means in concrete operational terms. A crew launches from Earth during one of the transfer windows that open roughly every 26 months. After approximately 7 months of transit, they arrive at Mars. They land. They begin surface operations. 6 weeks into the surface mission, a critical failure occurs. Perhaps the primary habitat develops a structural compromise. Perhaps the ascent vehicle's propulsion system shows an anomaly that could prevent it from reaching orbit when the time comes to leave. Perhaps a crew member suffers an injury severe enough that continued surface operations become untenable. On the station, any of these scenarios triggers an evacuation within days. At the Moon, a direct return is measured in roughly 72 hours. On Mars, the crew checks the orbital mechanics chart and finds that the next viable departure window is 14 months away. 14 months. Not because the spacecraft is broken, not because the fuel is insufficient, because the planets are in the wrong positions. Earth and Mars orbit at different speeds and different distances from the Sun, and the energy-efficient transfer trajectories that make the journey physically possible exist only when the geometry aligns. Miss the window, and the next one does not open for another 2 years. So the crew must survive those 14 months with whatever resources remain. If the habitat is compromised, they must repair it or relocate to a backup shelter, if one exists. If the ascent vehicle is suspect, they must diagnose and fix the propulsion anomaly with the tools and spare parts they carried, because no replacement engine is coming from Earth. If a crew member is injured, the remaining crew must provide long-term care in a medical facility the size of a closet, with a pharmacy that was stocked on Earth 2 years ago, while simultaneously maintaining all other mission operations with one fewer pair of hands. The surgical scenario sharpens this further. On Earth, an astronaut candidate who develops appendicitis goes to a hospital. On the station, the condition has never required emergency surgery, though contingency procedures exist, and the crew could potentially evacuate before the situation became critical. On Mars, evacuation is not an option. If a crew member's appendix ruptures, the mission's designated medical officer must perform an appendectomy. Not in a hospital, not in a sterile operating theatre with backup surgeons, anesthesiologists, and a blood bank. In a spacecraft habitat, under partial gravity, with instruments sterilized using onboard equipment, guided by training that may have been completed 2 or more years before the moment of crisis. The flight surgeon on Earth, if conjunction is not blocking the signal, will receive the crew's report roughly 12 minutes after it is sent, and will transmit guidance that arrives 12 minutes later. 24 minutes of latency during a surgical procedure where every minute matters. The crew has trained for this. They have practiced on simulated tissue. They have memorized protocols. But no analog on Earth fully replicates the combination of partial gravity, confined space, delayed communication, limited anesthesia, the knowledge that the patient is also a crew member whose skills are essential to the mission, and the awareness that if the procedure fails, there is no hospital, no second surgeon, and no helicopter arriving in 20 minutes. The crew must succeed with what they have, And what they have is training, tools, each other, and nothing else. Life support reliability becomes a matter of raw probability over time. NASA's own technical literature states that the probability of a fatal life support failure must remain below 1 in 1,000 across a multi-year deep space mission. That target sounds comfortable until you examine what it requires. The station's life support systems have experienced more failures than engineers originally expected. Components are regularly replaced, recalibrated, and upgraded using parts launched from Earth. The system works because the supply chain works. On Mars, the supply chain does not exist. Every replacement part must be carried from Earth at launch. Every redundant component adds mass, and mass costs fuel, and fuel determines whether the mission is physically possible within the limits of available rockets. Engineers address this through redundancy. Critical systems are duplicated or tripled. Spare components are packed alongside primary ones. Crews are trained to repair and rebuild hardware using available materials. But redundancy has limits. A 3-year mission exposes every system to roughly 26,300 hours of continuous operation. Seals wear, pumps fatigue, electronics drift. The longer the mission runs, the more the probability of failure compounds. A system that has a 99% chance of surviving 1 year has roughly a 97% chance of surviving 3. Stack enough systems together, each with its own independent failure probability, and the cumulative risk across the entire vehicle becomes a number that engineers study with considerable care. Radiation adds a slow, invisible clock to the mission. Beyond the protection of Earth's magnetosphere, astronauts are exposed to 2 primary sources of ionizing radiation. Galactic cosmic rays are high-energy particles, mostly protons and heavy atomic nuclei, that originate outside the solar system and penetrate spacecraft shielding with relative ease. They deliver a continuous low-level dose that accumulates over time. Solar particle events are sudden bursts of radiation emitted by the sun during solar flares and coronal mass ejections. These events can deliver large doses in a matter of hours. NASA's current career radiation exposure limit for astronauts is 600 millisieverts, a standard adopted in 2022 that applies equally regardless of age or sex. Estimates based on actual measurements from the Curiosity rover's radiation assessment detector suggest that a standard round-trip Mars mission would expose the crew to a cumulative dose of approximately 1,000 millisieverts, roughly 1 sievert. That does not merely consume a portion of NASA's 600 millisievert career limit. It exceeds the entire limit, and that estimate assumes typical conditions. A severe solar particle event during transit, when the crew is outside Earth's magnetic protection and the planet's bulk cannot serve as a shield, could add a significant additional dose in hours. The August 1972 solar event, which occurred during the gap between Apollo 16 and Apollo 17, produced particle fluxes that researchers estimate could have delivered potentially incapacitating or lethal doses to astronauts conducting a surface spacewalk on the Moon. A Mars crew caught in transit during a comparable event would have to shelter in the most heavily shielded section of the spacecraft and wait for the storm to pass, knowing that every hour of exposure accumulates damage at the cellular level that cannot be reversed. The radiation effects are not limited to cancer risk. Research conducted by NASA's Human Research Program has identified potential impacts on the central nervous system from heavy ion exposure, including cognitive decline, impaired decision-making, and altered behavior. Animal studies suggest that galactic cosmic ray exposure can produce measurable changes in brain structure and function. The relevance of these findings to human crews on multi-year missions is still being studied, but the possibility that radiation could subtly impair the judgment of the very people who must make life or death decisions without ground support is among the more unsettling aspects of the Mars problem. And then there is the psychological dimension, which is perhaps the least visible and most corrosive threat of all. Isolation studies conducted in analog environments on Earth, sealed habitats designed to simulate the conditions of a Mars mission, have documented predictable patterns of psychological strain. Crew members experience a phenomenon researchers call the third quarter effect, a period of declining morale and increased interpersonal tension that tends to occur roughly 3/4 of the way through a mission. On the station, astronauts cope with 6-month rotations supported by regular communication with family, video calls with psychologists, care packages from Earth, and the knowledge that their return date is weeks or months away. Even with all of that support, behavioral studies have documented gradual declines in crew cohesion, increased friction between crew and ground controllers, and a phenomenon sometimes described as psychological closing, where astronauts become less forthcoming with ground teams as the mission progresses. A Mars crew would face a qualitatively different psychological landscape. Communication with family would be limited to recorded messages with minutes or hours of delay. No real-time video calls, no spontaneous conversations. Every exchange would have the cadence of letters, not dialogue. The crew would live and work with the same small group of people for 2 to 3 years in a confined space, roughly the size of a small house, with no ability to leave, no new faces, no change of scenery, and the growing awareness that Earth is receding not just in distance, but in relevance. If interpersonal conflict develops, there is no transfer, no reassignment, no separation. The crew must resolve it or endure it. There is no third option. What makes the psychological challenge different from the engineering challenges is that it does not present as a discrete failure. A pump breaks or it does not. A seal holds or it does not. Psychological degradation is gradual. It erodes judgment, patience, and cooperation over months. A crew member whose decision-making has been subtly impaired by isolation, sleep disruption, and chronic stress may not recognize the impairment. And the ground team, which on station missions can detect behavioral changes through daily private conferences and real-time observation, will be monitoring the Mars crew through time-delayed messages that reveal only what the crew chooses to share. The safety net that catches early signs of psychological trouble on the station, the direct, immediate human connection between crew and ground, is precisely the thread that delay cuts first. This is not speculation built from theory. It has been tested. In 2010, 6 men entered a sealed facility at the Institute of Biomedical Problems in Moscow and did not come out for 520 consecutive days. The experiment was called Mars 500, and it remains the highest fidelity ground simulation of a crewed Mars mission ever conducted. The facility was designed to mimic a spacecraft. The timeline was structured to replicate the phases of a real mission. Roughly 250 days of simulated outbound transit, 30 days of orbital operations, including a simulated Mars landing, and 240 days of return transit. Communication with the outside was artificially delayed by 20 minutes in each direction, matching the average signal lag between Earth and Mars. The crew of 3 Russians, 1 Frenchman, 1 Italian, and 1 Chinese volunteer lived and worked under these conditions for the full duration without interruption. No one suffered a psychotic break. No one attempted to leave. On the surface, the mission was a success, but the data published across multiple peer-reviewed journals in the years that followed told a more complicated story. Sleep quality deteriorated for most of the crew. Circadian rhythms drifted out of alignment. 1 crew member became progressively sedentary as the mission continued, eventually spending the majority of his time in his sleeping compartment. Physical activity declined across the group. Alertness dropped. The crew exhibited a pattern consistent with the third quarter phenomenon described in earlier isolation research. A measurable decline in mood and engagement that deepened as the mission passed its midpoint and the simulated return to Earth still felt distant. The communication delay, though artificial, produced effects that researchers found particularly revealing. When psychological support from the outside was filtered through a 20-minute lag, it lost most of its therapeutic immediacy. A crew member experiencing frustration or anxiety could not talk through the moment with a psychologist in real time. By the time a response arrived, the emotional context had shifted. The support felt disconnected from the need. Mission control in Moscow was deliberately limited to an observational role during the simulated deep space phases, and crew members later described those periods as the moments when the simulation felt most real. The delay did not just slow the conversation, it severed the sense that someone on the other side was present in the same moment. And these 6 volunteers had advantages that a real Mars crew would not. They lived in full Earth gravity. They breathed air that did not depend on recyclers. They faced no radiation. They knew at every moment that in a genuine emergency, someone could open the hatch from the outside and pull them out. The psychological effects they exhibited emerged despite the presence of that ultimate safety net. Remove it, place the crew in actual deep space with actual consequences, and the pressures documented in Moscow become the baseline, not the ceiling. Consider what happens when multiple threads fray at the same time. A crew member develops a condition requiring medication that has degraded below effective potency after 2 years of radiation exposure. The crew consults a flight surgeon on Earth across a 28-minute round-trip delay. The condition worsens during the wait. A second crew member, fatigued by months of confinement, makes an error reconfiguring a backup life support component, triggering a secondary malfunction. The ground team, learning about the original medical problem 14 minutes after it was reported, transmits guidance that arrives after the second malfunction has already occurred. The situation has evolved past the ground's understanding before the ground's advice reaches the spacecraft. This is not a dramatic Hollywood scenario. It is a systems analysis of what happens when communication delay compounds with equipment degradation, pharmaceutical limitations, psychological strain, and the absence of resupply. Each factor alone is manageable. Together across 2 to 3 years, they form a web of interacting risks that no ground team can untangle in real time because real time no longer exists between the 2 planets. NASA's rover missions on Mars offer a small-scale preview of how delay shapes operations. The Perseverance rover cannot be driven like a remote control vehicle. Each morning, engineers at the Jet Propulsion Laboratory plan a full Martian day of activities, upload a command sequence, and then wait for the results to arrive hours later. The rover carries autonomous hazard avoidance software because a rock that appears in its path cannot be reported to Earth and addressed in time. The rover must decide for itself whether to stop or navigate around the obstacle. Every command sent to Mars is essentially a letter mailed to a machine that cannot ask for clarification. Human crews on Mars will operate under the same constraint. Mission Control will not manage the mission. It will advise the mission, with advice that arrives minutes to hours after the moment it was needed. The crew must internalize the expertise that the ground currently provides. They must become their own flight controllers, their own flight surgeons, their own engineers, their own psychologists. Not because Earth lacks the experts, because the distance between Earth and the experts has grown so large that the knowledge arrives too late. This is the transformation that Mars demands. Every previous crewed mission in history has operated within a framework where the ground and the crew function as a single system. The ground monitors, the ground decides, the ground corrects. That framework depends on latency measured in seconds or less. Mars shatters the framework. What replaces it is a crew that must function as an autonomous unit, making decisions, diagnosing failures, treating injuries, and managing crises with the knowledge and tools they carry and nothing more. The terrifying part is not that this is impossible. It may well be achievable with sufficient training, redundancy, and crew selection. The terrifying part is what it reveals about the nature of distance. Every mile between the spacecraft and Earth is a mile of silence. Not the silence of empty space, but the silence of unreachable help. The experts still exist. The hospitals still exist. The supply chains still exist. They are all still there on Earth, fully operational, fully capable. But they might as well be imaginary because the distance has turned them into memories of a support system that can no longer support. And Mars, for all its danger, still sits within the sun's inner neighborhood. The signal delay is measured in minutes. The journey home, though constrained by orbital mechanics, takes months rather than years. The sun still provides measurable warmth and usable light. Power from solar panels is diminished but not negligible. The crew can still see Earth through a telescope, a bright point in the Martian sky, steady and blue and impossibly far away, but still identifiable as home. Beyond Mars, even those thin comforts disappear. The outer solar system is a region where the sun fades from a blazing disk to a distant bright dot, where solar power drops to fractions of a percent, where communication delays stretch from minutes into hours, where temperatures plunge towards the baseline cold of deep space, and where the only human-made objects that have ever traveled are machines that carry no crew, no life support, and no way home. What waits out there is not a worse version of the Mars problem. It is a different category of isolation entirely, and the machines we send to explore it are now teaching us, in real time, what it looks like when the last threads of the safety net dissolve one by one. Past the orbit of Mars, the solar system opens into something that the human mind is not built to comprehend. The distances between objects stop being large and become absurd. Mars orbits at roughly 1.5 astronomical units from the Sun, where 1 astronomical unit is the distance between the Earth and the Sun, approximately 93 million miles. Jupiter orbits at 5.2 astronomical units, Saturn at 9.5, Uranus at just over 19, Neptune at 30. The gaps between these worlds are not like the gap between Earth and the Moon, or even Earth and Mars. They are chasms so wide that light itself, the fastest thing the laws of physics permit, needs hours to cross them. And out here, the sun begins to fail you. Not dramatically, not all at once. It does not vanish behind a curtain. It shrinks. From Earth, The sun fills roughly half a degree of sky, a blazing disk that heats the surface to temperatures sustaining liquid water, weather, and life. At Jupiter's distance, the sun appears roughly 1/5 the diameter it shows from Earth, still clearly the brightest object in the sky, but the light it delivers has dropped to approximately 4% of what Earth receives. At Saturn, the figure drops to roughly 1%. At Uranus, about 1/4 of 1%. At Neptune, roughly 1/9 of 1%. By the time you reach the outer edge of the solar system, the sun is indistinguishable from a very bright star. It is still the brightest point in the sky, but it no longer feels like a sun. It feels like a memory of one. This is not poetry. It is an engineering crisis. Solar panels, the primary power source for every crewed spacecraft, and most robotic ones inside the orbit of Mars, become effectively useless beyond the asteroid belt. The mathematics are unforgiving. Solar panel output drops with the square of the distance from the sun. Double the distance, and you receive 1/4 the power. Triple it, and you receive 1/9. At Jupiter's distance, a solar array that produces 10,000 watts near Earth would produce roughly 400. At Saturn, roughly 100. At Neptune, roughly 10. You cannot sustain a human crew on 10 watts. You cannot run a life support system, recycle water, scrub carbon dioxide, regulate temperature, or power communications on the trickle of sunlight that reaches the outer planets. Every spacecraft that has operated in the outer solar system has relied on nuclear power, specifically on devices called radioisotope thermoelectric generators, which convert the heat produced by the natural decay of plutonium-238 into electricity. These generators have no moving parts, require no maintenance, and are extraordinarily reliable, and they are slowly dying from the moment they are built. Plutonium-238 has a half-life of approximately 87.7 years. That means after roughly 88 years, half the original plutonium has decayed, and the generator produces roughly half its original thermal output. But the electrical degradation is faster than the isotope decay alone, because the thermoelectric elements that convert heat to electricity also degrade over time. The junctions corrode, thermal conductivity changes. The overall power output of a radioisotope generator drops measurably every year, and this decline is permanent and irreversible. There is no way to refuel it. There is no way to replace the thermoelectric elements in deep space. The power curve slopes downward from launch day until the generator can no longer sustain the systems connected to it. The most vivid demonstration of what outer solar system communication delay means for a real mission occurred in July 2015 when NASA's New Horizons spacecraft attempted the first ever flyby of Pluto. The spacecraft had been traveling for 9.5 years to reach the dwarf planet, roughly 3 billion miles from Earth. At that distance, a one-way radio signal took approximately 4 hours and 27 minutes to arrive. A round trip, command and confirmation took roughly 9 hours. 10 days before the flyby, with the spacecraft hurtling toward Pluto at over 30,000 miles per hour, New Horizons suffered a critical glitch. An onboard anomaly caused the spacecraft to enter protective safe mode, switching from its primary computer to a backup and cutting off contact with Earth for 1 hour and 19 minutes. When the signal returned, engineers discovered that the glitch had wiped out the entire flyby command sequence, the meticulously choreographed set of science observations that New Horizons was supposed to execute during its brief window at Pluto. The flyby would last only a few hours. The spacecraft would pass within roughly 7,800 miles of the surface, and then continue outward, never to return. There would be no second chance. The mission's lead scientist later described what followed as a chess match with a 9-hour time delay. Engineers had to rebuild the entire command sequence from scratch, a task that would normally take weeks, and upload it to a spacecraft 3 billion miles away through a communication link that imposed a 4.5-hour wait on every instruction. They could not test the sequence in real time. They could not watch the spacecraft respond and adjust. They sent commands, waited hours to learn whether they worked, made corrections, and sent more. The team worked without sleep for 76 consecutive hours. They restored the flyby software with 4 days to spare. On July 14th, New Horizons executed its flyby autonomously. The spacecraft was on its own. No ground controller could intervene during the encounter, because by the time any signal reached the spacecraft, the flyby would have been over for hours. The observation sequence ran without a single error. New Horizons captured the first close-up images of Pluto's surface, revealing ice mountains, nitrogen glaciers, and a heart-shaped plain that will become one of the most iconic photographs in planetary science. But the ground team did not see any of this in real time. After the closest approach, New Horizons fell silent for nearly 13 hours as it oriented its antenna back toward Earth and began transmitting. The engineers waited, unable to know whether the encounter had succeeded or failed, watching clocks and hoping. When the confirmation signal finally arrived, it carried a simple message. The autonomous sequence had completed. No anomalies had occurred. The mission had worked. And then the data came. Slowly. At a trickle. The total dataset from the Pluto flyby took over 15 months to transmit back to Earth, because at 3 billion miles, the data rate had been reduced to the point where a single photograph took hours to download. New Horizons had gathered more than 50 gigabits of data during its brief encounter, and it delivered that data to Earth one slow stream at a time across the better part of 2 years. That was a robotic flyby. No lives were at stake, no air needed to be recycled, no food needed to be rationed, and still, a single glitch 10 days before the encounter nearly destroyed the mission. And the only reason it did not was that a team of engineers on Earth was willing to work for 3 days without rest to rebuild a command sequence through a communication link that imposed a 9-hour round trip on every exchange. The Voyager spacecraft are the most vivid illustration of this constraint. Voyager 1 and Voyager 2 each launched in 1977, carrying 3 radioisotope thermoelectric generators apiece. At launch, each spacecraft's generators produced roughly 470 watts of electrical power. That is less than the power consumed by a standard household hairdryer. The entire electrical budget of humanity's farthest traveling machines was, from the beginning, barely enough to run a handful of instruments, a radio transmitter, a computer with less processing power than a modern key fob, and the heaters needed to keep critical components from freezing. Nearly 5 decades later, that power has dropped to roughly 220 watts per spacecraft, less than half the original output. And the decline continues at a rate of roughly 4 watts per year. To keep the most essential systems running, NASA's engineers at the Jet Propulsion Laboratory have been shutting down instruments one by one, triaging the spacecraft's dwindling power the way a field medic triages patients. In April 2026, engineers shut down Voyager 1's low-energy charge particles experiment to conserve power. The spacecraft was over 15 billion miles from Earth at the time. The command to shut down the instrument took approximately 23 hours to arrive. The shutdown procedure itself required more than 3 hours. Confirming that it worked required waiting another 23 hours for the telemetry to travel back. Each instrument shutdown extends the mission's life by a small margin, but the trajectory is clear. Sometime in the early to mid-2030s, Voyager 1 will no longer have enough power to operate any scientific instruments at all. Shortly after that, the transmitter will fall silent. The spacecraft will continue moving outward, carried by its own momentum, but it will become deaf and mute. A dark object drifting through interstellar space with no ability to communicate. No ability to sense its surroundings, and no ability to respond to any signal from Earth. It will become, in the most literal sense, a message in a bottle that can no longer be read. Voyager will not be the first spacecraft to go silent. That distinction belongs to its predecessors, Pioneer 10 and Pioneer 11, the first human-made objects to cross the outer solar system. Pioneer 10 launched in 1972 and became the first spacecraft to fly through the asteroid belt and past Jupiter. Pioneer 11 followed in 1973, visiting Jupiter and then making the first direct observations of Saturn. Both carried the same type of radioisotope power source as the Voyagers. And both eventually fell silent, not because they were destroyed, but because their power decayed below the minimum needed to sustain a detectable signal. Pioneer 11 went first. Its mission ended on September 30th, 1995, when the last transmission was received. Earth's motion had carried the planet out of the spacecraft's antenna beam, and without propulsion to reorient itself, Pioneer 11 could no longer point its transmitter toward home. Whether the spacecraft continued to broadcast after that date is unknown. No signal was ever received again. It is still out there, drifting outward, carrying a gold plaque engraved with images of a man and a woman and a diagram showing Earth's position relative to 14 pulsars. It carries this message into a silence that began over 30 years ago and will last forever. Pioneer 10 held on longer. Its faint signal was tracked by the Deep Space Network for years after its science mission officially ended. By the early 2000s, the spacecraft was over 7.6 billion miles from Earth, and its signal took more than 11 hours to arrive. The last confirmed telemetry came on April 27th, 2002. The last detectable signal, too faint to carry any data, was received on January 23rd, 2003. NASA attempted contact once more in March of 2006. Nothing came back. Pioneer 10 is now a ghost ship, coasting silently toward the red star Aldebaran in the constellation Taurus. It will take more than 2 million years to arrive. No one will be listening when it does. The fate of the Pioneers is a preview of what awaits every spacecraft that ventures far enough from the sun. Power fades, signals weaken, components degrade. And at some point, the whisper from the machine becomes too faint for even the largest antennas on Earth to detect. The spacecraft does not die in any dramatic sense. It simply becomes undetectable. It crosses a threshold, not of distance exactly, but of signal strength, below which it vanishes from human awareness as completely as if it had never existed. The machine is still there. It is still moving. It may still be trying to transmit. But from Earth's perspective, it is gone. beyond the outer planets, beyond the orbits of Neptune and Pluto, past the region where the Pioneers and Voyagers are drifting, the solar system does not simply end. It dissolves into a vast, sparsely populated shell of icy objects called the Oort cloud, a theoretical reservoir of trillions of comets extending from roughly 2,000 astronomical units from the Sun at its inner edge to perhaps 100,000 astronomical units at its outer edge, with that far boundary reaching roughly 1.5 to 2 light years from home. A spacecraft leaving Neptune's orbit would enter this region and travel through it for centuries, possibly millennia, before emerging on the other side. During that crossing, there would be effectively nothing. No planets, no moons, no asteroid fields dense enough to see, only the occasional frozen body separated from its nearest neighbor by millions of miles of empty space. A crew crossing the Oort cloud would experience the purest form of isolation the solar system can produce, too far from the sun for it to appear as anything more than a bright star, too far from the nearest neighboring star for it to appear as anything more than a slightly different bright star, suspended in a darkness so complete that the only light visible through the windows would be the ancient light of distant galaxies and the cold, unchanged constellations of the Milky Way. But before that silence arrives, Voyager 1 is about to cross a milestone that frames the isolation problem in the starkest possible terms. In November of 2026, Voyager 1 will become the first human-made object to reach a distance of 1 light day from Earth. 1 light day. The distance that light, traveling at 186,000 miles per second, covers in 24 hours. Approximately 16.1 billion miles. At that distance, a command sent from the Jet Propulsion Laboratory on a Monday morning will not arrive at the spacecraft until Tuesday morning. If Voyager 1 responds immediately, the confirmation will not reach Earth until Wednesday morning. Susie Dodd, the Voyager project manager, described the cadence in concrete terms. If she sends a message saying good morning to Voyager 1 at 8 a.m. on Monday, she will receive the spacecraft's response at approximately 8 a.m. on Wednesday. 2 full days for the simplest possible exchange. Not because the technology is slow, because the distance is vast and light is the fastest messenger the universe allows. Now imagine a crew at that distance, not a machine with no biological needs, but human beings who must breathe every few seconds, drink every few hours, eat every day, and sleep every night. A crew whose air recycler has malfunctioned. They report the failure. 24 hours later, Mission Control receives the report. Engineers spend several hours diagnosing the problem and preparing instructions. They transmit the fix. 24 hours later, the crew receives it. If the fix works, they report success. 24 hours later, Mission Control confirms. The total time from failure report to confirmed resolution is a minimum of 3 days. 3 days in which the crew must either solve the problem themselves or manage their remaining breathable air. A carbon dioxide scrubber failure at this distance is not the same emergency it would be on the station, where the ground team responds in seconds. It is not even the same emergency it would be on Mars, where the ground responds in minutes. At 1 light day, the ground does not respond in any time frame that matters for the immediate survival of the crew. The crew is alone. The word alone does not mean lonely. It means unsupported. It means that every diagnosis, every repair, every decision about whether to ration air or attempt to fix must happen inside the hull, in real time, without consultation. No second opinion arrives for 2 days. No alternative procedure is transmitted overnight. The only spare parts that exist are the ones packed in the cargo hold. Everything else, every expert, every warehouse, every hospital, every factory is a day away at the speed of light, which means it is a lifetime away for any emergency that must be resolved in hours. The communication challenge is compounded by the signal strength problem. Radio signals weaken with distance according to the inverse square law. Double the distance, and the signal arriving at the receiver is 4 times weaker. At the distances involved in the outer solar system and beyond, the signals from a spacecraft become extraordinarily faint. The radio signal arriving from Voyager 1 at NASA's Deep Space Network antennas is measured in fractions of a billionth of a watt. To receive it, the Deep Space Network uses dish antennas up to 70 meters in diameter, positioned at 3 sites spaced equally around the globe in California, Spain, and Australia, so that at least one facility always has a line of sight to any point in the sky as Earth rotates. Even with these enormous antennas, the data rate from Voyager 1 has been reduced over the decades to a trickle. In the early mission, during the Jupiter and Saturn flybys, Voyager transmitted data at rates sufficient to send images in near real time. Today, the data rate has been reduced to roughly 160 bits per second. For comparison, a typical home internet connection operates at millions or tens of millions of bits per second. Voyager sends data at a pace that would take hours to transmit a single photograph. The communication link is not a conversation. It is a whisper, carried across billions of miles by a transmitter running on the power output of a dim light bulb, received by an antenna the size of a football field. A crewed mission at these distances would require a dramatically more powerful communication system, but the physics imposes hard limits. Larger antennas, higher powered transmitters, and laser communication systems can improve the link, but they cannot eliminate the delay. And every increase in communication capability adds mass and power requirements to a spacecraft that is already struggling with both. The engineering trade-offs become severe. More power for communication means less power for life support, or more mass for larger generators, which requires more fuel, which requires a larger spacecraft, which requires more power to sustain. The spiral is relentless. Thermal control adds another layer to the problem. In the inner solar system, spacecraft must manage excess heat. Near the sun, temperatures on exposed surfaces climb to hundreds of degrees. The challenge is keeping the interior cool enough for equipment and crew to function. In the outer solar system, the problem reverses entirely. The background temperature of deep space is approximately minus 455 degrees Fahrenheit, just a few degrees above absolute zero. Without sunlight to warm the exterior, a spacecraft must generate all of its own heat. Every watt dedicated to heating is a watt unavailable for life support, communication, or propulsion. Insulation helps, but it is not perfect. Heat leaks outward through every surface, every window, every structural connection. The spacecraft becomes a warm island in an ocean of cold, constantly bleeding energy into the void. The Voyager spacecraft carries small radioisotope heaters, devices that use the decay heat of plutonium to keep critical components above their minimum operating temperatures. Without these heaters, the spacecraft's fuel lines would freeze, its electronics would fail, and its scientific instruments would become inoperable. The heaters consume no electrical power, relying instead on passive radioactive decay. but they represent mass that must be accounted for in the spacecraft's design. A crewed vessel at these distances would need heating on a vastly larger scale, enough to maintain a habitable temperature across living quarters, workspaces, and storage areas for years. The energy cost would be enormous and constant. Navigation in the outer solar system presents challenges that do not exist closer to home. Near Earth, spacecraft navigate using a combination of ground-based tracking, satellite positioning, and known reference points. The Deep Space Network can determine a spacecraft's position, velocity, and trajectory with extraordinary precision by measuring the time delay and frequency shift of radio signals. But this technique requires a functioning communication link and a ground team that can process the data and transmit corrections. At distances where the round-trip signal time is measured in hours, the crew cannot rely on ground-based navigation for time-sensitive maneuvers. An engine burn planned for a specific moment must be calculated and executed by the crew, with the results confirmed by the ground only hours later. If the burn was incorrect, the correction comes too late to prevent the trajectory error from compounding. Interplanetary probes handle this through careful pre-planning and autonomous onboard navigation systems. The spacecraft carries star trackers, sensors that identify the positions of known stars and use them to determine orientation. But star tracking provides attitude information, the direction the spacecraft is pointing, not position information where it actually is in space. Position determination still depends on radio tracking from Earth. A crewed vessel in the outer solar system would need more sophisticated autonomous navigation, possibly incorporating optical measurements of known solar system objects and onboard computation of trajectories. These systems exist in concept but have never been tested at the scale required for a crewed, deep space mission. There is another dimension to the outer solar system that rarely appears in engineering documents, but weighs heavily on anyone who thinks carefully about what it would mean to send humans there. It is the dimension of perception, of what it looks and feels like to be that far from home. On the station, astronauts look out the cupola windows and see Earth filling the frame. Blue oceans, white clouds, green continents, the Terminator line between day and night sweeping across familiar geography. They can identify their home countries. Some have reported seeing the glow of cities at night. The planet is enormous and close and present. It dominates the visual field and the emotional landscape of the mission. Home is right there. From the moon, Earth is smaller but still breathtaking. The Apollo crews describe the site as transformative. A bright blue marble hanging in the black sky, visibly alive, visibly fragile, 4 times the apparent diameter of the full moon as seen from Earth. The astronauts could cover it with an outstretched thumb, but it was still unmistakably theirs. Still close enough to see the continents. Still close enough to feel connected to. From Mars, Earth is a bright point of light in the evening or morning sky. The Curiosity rover has photographed it from the surface. It appears as a small dot, clearly visible but no longer showing any detail. No continents, no oceans, no evidence of civilization, just a point of light among the stars, distinguished only by its brightness and its position. Astronauts on Mars would know intellectually that everyone they have ever loved lives on that dot. But the dot would not look like home. It would look like a star. From Jupiter, Earth becomes difficult to find without knowing exactly where to look. From Saturn, it is a pale speck so faint that the rings of Saturn would dominate the visual field, while the place you were born from is lost in the background noise of distant stars. From the distance of Voyager 1, Earth is invisible to any instrument the spacecraft carries. In 1990, Voyager 1 turned its camera backward and captured the famous pale blue dot photograph. Earth appeared as a tiny fleck, less than a single pixel across, caught in a band of scattered sunlight. The astronomer Carl Sagan described it as a mote of dust, suspended in a sunbeam. That image was taken from approximately 3.7 billion miles. Voyager 1 is now more than 4 times farther away. If its cameras were still operational, Earth wouldn't register at all. This visual disappearance is not merely symbolic. It has documented psychological effects. Research into isolation and confinement in analog environments has identified the severing of visual connection to home as a significant stressor. On the station, the sight of Earth provides a continuous, involuntary reminder that home exists, that the mission has a destination, that the world the astronauts left behind is real and present. On a mission to the outer solar system, that visual anchor dissolves. Earth becomes an abstraction, a coordinate, a memory that the crew must actively maintain because the universe no longer reinforces it. The Voyager spacecraft do not care about this. They are machines. They do not experience loneliness or disorientation or the slow erosion of purpose that comes from losing sight of the reason you left. They transmit their data, execute their commands, and drift outward in perfect mechanical indifference. The spacecraft will continue functioning until their power runs out, and then they will continue drifting forever, carrying a golden record etched with sounds and images of Earth, a message to anyone who might find them millions of years from now. But a crewed mission is not a machine. It is a collection of human beings who need more than air and water and calories to survive. They need purpose. They need connection. They need the belief that what they are doing matters and that someone is listening. In the outer solar system, the connection to Earth becomes a thread so thin that it can only be maintained through deliberate effort, through scheduled communication sessions planned days in advance, through recorded messages exchanged with families who will not hear the response for hours, through a mission control team whose role has shifted from directing the mission to witnessing it. The Voyager missions teach one more lesson that is essential to understanding what lies beyond. It concerns time. Not signal delay, but the passage of years and what those years do to a machine that cannot be repaired. Voyager's 47 years of continuous operation have produced one of the longest records of electronic degradation in deep space ever assembled. NASA's own mission updates document a systematic decline across multiple component categories. Power output has fallen by more than half from launch day levels. Transmitter strength has weakened measurably. Sensor calibrations have drifted enough to require periodic correction from the ground. The degradation follows patterns consistent with both random failure and cumulative wear, meaning that as the mission ages, systems become progressively more likely to fail simply because of accumulated use and exposure to the deep space radiation and thermal environment. These are the realities of long-duration spaceflight expressed in cold telemetry. Every machine ages. Every component drifts toward failure along a curve that begins the moment it is manufactured. Near Earth, aging is managed through maintenance, replacement, and upgrade. The station has been continuously maintained for over 25 years. Components that wear out are replaced. Systems that become obsolete are upgraded. The station survives because it is continuously renewed by the supply chain connecting it to Earth. In the outer solar system, the supply chain does not exist. A spacecraft carries its original components and its spare parts, and when those are exhausted, the aging process becomes the mission's clock. Not the clock that measures days and hours, but the clock that measures how many failures the vehicle can absorb before a critical system degrades past the point of recovery. For the Voyager probes, this clock is winding down gracefully. The spacecraft were designed for a 4-year mission and have lasted nearly 50. The engineering is extraordinary, but the end is approaching. Each year, another instrument goes dark. Each year, the power margin shrinks. Each year, the engineers on the ground have fewer options and longer waits between command and response. For a crewed mission, the same clock would run with a different urgency. A machine can wait 3 days for a command. A human being cannot wait 3 days for breathable air. The degradation curves that Voyager endures with mechanical patience would impose biological deadlines on a crew that no engineering margin can fully absorb. This is what the outer solar system reveals, not a new category of danger, but the final erosion of the framework that made danger survivable. Near Earth, danger is managed by real-time communication, rapid rescue, continuous resupply, and deep institutional expertise. At the Moon, rescue slows but remains possible. At Mars, communication delay makes ground support unreliable and return depends on orbital mechanics. In the outer solar system, every remaining thread of that framework fails. Communication becomes a correspondence measured in hours or days. Rescue is not slow, it is non-existent. No spacecraft can be launched from Earth and reach the outer planets in time to respond to any emergency that unfolds on a human timescale. Resupply is impossible. Expertise exists only inside the crew's own minds. And the spacecraft itself, the only barrier between the crew and the void, is aging every day, every hour, every minute, trending along degradation curves that bend toward failure with the patience of physics. Voyager 1 will cross the 1 light day threshold in November 2026, and it will keep going. It will not stop. It will not slow down. It is traveling at roughly 38,000 miles per hour, and there is nothing in its path to impede it for billions of years. It will leave the sun's gravitational neighborhood. It will enter the space between stars, and it will continue outward into a region where the sun is just another star in a crowded sky, where no signal from Earth arrives within a day, then a week, then a month, then a year. The spacecraft will not care. It is a machine. But behind it, on a small blue planet orbiting an ordinary yellow star, a species is watching its farthest emissary disappear and asking whether it has the courage to follow. And what waits in that direction, the direction Voyager is traveling, is not more space. It is the place where the last connection to Earth finally breaks. Where the word home stops meaning a place you can return to and starts meaning a place you remember. Where every system a mission depends on must be carried, maintained, repaired, and rebuilt by the people inside the vessel. For years, for decades, for generations, with no resupply, no rescue, no reinforcement, and no voice from the ground arriving in time to matter. That is interstellar space. And the distance to the nearest star makes everything in this story so far look like a walk across the room. Proxima Centauri is the nearest star to our sun. It sits approximately 4.24 light-years away. That number deserves to be unpacked because it contains a truth that most people absorb intellectually, but never feel. 1 light-year is the distance light travels in 1 year, Light moves at roughly 186,000 miles per second. In a single year, it covers approximately 5.88 trillion miles. Multiply that by 4.24, and you arrive at the distance to the nearest star, roughly 25 trillion miles. A number so large that writing it does nothing to convey what it means. Here is what it means. Voyager 1, the farthest human-made object in existence, has been traveling at roughly 38,000 miles per hour since its Saturn flyby in 1980. It has been moving outward for nearly 50 years without stopping. And in all that time, it has covered less than 0.1% of the distance to Proxima Centauri. At its current speed, Voyager 1 would need over 73,000 years to reach the nearest star. 73,000 years. Human civilization, everything from the earliest permanent settlements to this sentence, fits inside roughly 10,000 years. Voyager would need 7 times that span just to reach the closest neighboring sun. The Parker Solar Probe, which holds the record for the fastest speed ever achieved by a human-made object during its closest passes to the sun, reaches a peak velocity of roughly 430,000 miles per hour. Even at that extraordinary speed, the journey to Proxima Centauri would take approximately 6,300 years. That is older than the Egyptian pyramids, older than written language, a journey that will begin before the invention of the wheel and end long after every nation, language, and institution on Earth today has been forgotten. These numbers are not presented to inspire awe. They are presented to establish a fact. Interstellar space is not far the way Mars is far. It is not far the way Jupiter or Saturn, or even the edge of the solar system is far. It is far in a way that breaks the concept of travel as humans understand it. A one-way signal from a spacecraft at Proxima Centauri would take 4 years and 3 months to reach Earth. A reply would take the same. The simplest exchange of information, a single question and a single answer, would span 8.5 years. A crew that departed Earth and arrived at the nearest star would send their arrival message home and then wait nearly a decade to learn whether anyone heard it. At this distance, communication does not merely degrade, it ceases to function as communication in any human sense of the word. A message that takes 4 years to arrive is not a conversation. It is a time capsule. By the time the crew's report reaches Earth, the political leadership that authorized the mission may have changed. The engineers who designed the spacecraft may have retired or died. The language the report is written in may have drifted enough that idioms and references no longer land the same way. And the crew's situation, whatever it was when they pressed transmit, has evolved through 4 years of events that Earth knows nothing about. The ground cannot advise because the ground is responding to a reality that is 4 years out of date. The crew cannot request because any request will be answered 4 years after it was needed. This is the point at which the concept of mission control ceases to exist. Not because the building in Houston has been demolished, not because the engineers have stopped caring, but because the distance has created a temporal chasm so wide that the two parties, crew and ground, are living in different versions of history. They share a past, but not a present. The crew's present is the ground's future. The ground's present is the crew's past. The threads of communication still technically exist, photons still cross the void, but the connection they represent has become ceremonial. A letter exchanged between two people who will never again occupy the same moment. Every survival system that degraded across the journey so far now reaches its endpoint. Voice, which was instant on the station, delayed by seconds at the moon, delayed by minutes on Mars, and delayed by hours in the outer solar system, is now delayed by years. Rescue, which was possible in hours from the station, possible in days from the moon, physically irrelevant from Mars, and absurd from the outer planets, is now a word without operational content. No rescue vehicle can be designed, launched, and delivered to a crew 4 light years away. The concept does not translate to this distance. It belongs to a different category of spaceflight, one bounded by the reach of Earth's gravity and infrastructure, and interstellar space is outside that boundary by a factor of thousands. Resupply follows the same logic. A cargo shipment launched from Earth toward a crew at Proxima Centauri would take decades or centuries to arrive, depending on the propulsion technology available. The crew that requested the supplies would have lived and died and been succeeded by generations of descendants before the shipment appeared. Return is similarly transformed. A crew that departs for the nearest star does not plan to come home. Even if the spacecraft carries enough fuel for a round trip, the journey takes so long that the people who return are not the people who left. They are their children, or their grandchildren, or their great-grandchildren. The mission does not have a return date. It has a lineage. This reality forces a complete reimagining of what a spacecraft is. Near Earth, a spacecraft is a vehicle. It carries people from one place to another and brings them back. At Mars distance, a spacecraft is a habitat. It must sustain a crew for years without external support. At interstellar distances, a spacecraft is something else entirely. It is a world. The concept of a generation ship, a vessel designed to sustain a human population across centuries or millennia of transit, has been explored in science fiction for decades. But the engineering requirements are not fictional. They are calculable, and they are staggering. A generation ship must provide everything a civilization needs to survive indefinitely, with no external input of any kind. Air, water, food, energy, medicine, education, governance, reproduction, waste processing, psychological stability, cultural continuity, material repair, genetic diversity. Every function that Earth performs for its inhabitants must be replicated inside a sealed container moving through a vacuum at temperatures near absolute zero, for longer than most civilizations in human history have lasted. The food problem alone is immense. A crew cannot carry enough pre-packaged food for a journey lasting thousands of years. The food must be grown on board. This requires soil or hydroponic systems, artificial lighting powered by nuclear sources, water cycling, nutrient management, pest control without external ecosystems, seed preservation across generations, and agricultural knowledge maintained without interruption for centuries. A single crop failure lasting more than one growing season could cascade into famine. The medical problem scales with time. On the station, a crew member with appendicitis can be evacuated to a hospital. On Mars, the crew's physician must perform the surgery. On a generation ship, the medical system must handle every condition that can affect a human body across a lifespan, multiplied by every individual in the population, sustained across generations, with no ability to manufacture pharmaceuticals from scratch unless the ship carries a complete pharmaceutical production chain, which in turn requires chemical precursors, laboratory equipment, quality control, and expertise that must be taught and retaught across generations without institutional decay. The repair problem is perhaps the most fundamental. Every mechanical system fails given enough time. Seals degrade, metals fatigue, electronics drift and burn out. Insulation crumbles, lubricants break down. On a journey lasting centuries, every component of the ship will need to be replaced multiple times. This means the ship must carry not just spare parts, but the tools to make spare parts. Not just tools, but the raw materials to make tools. Not just raw materials, but the mining and refining capability to process raw materials from whatever sources might be encountered along the way, which in interstellar space means essentially nothing. The ship must be a complete industrial ecosystem, capable of manufacturing any component it needs from basic elements, indefinitely. The genetic problem is one that mission designers have studied with mathematical precision. A research paper analyzing the minimum viable population for an interstellar voyage calculated that a generation ship would need an initial crew of at least several hundred carefully selected individuals to maintain sufficient genetic diversity across thousands of years of travel. Below that threshold, inbreeding depression would reduce the population's fitness over generations, increasing vulnerability to disease and reducing reproductive success. The population must be managed with a reproductive strategy that preserves genetic diversity without imposing controls so rigid that they generate social conflict. The psychological problem extends beyond isolation into something deeper. It's the problem of purpose across generations. The people who board the ship at departure chose to go. They carry the motivation, the training, and the emotional connection to the mission's origin on Earth. Their children, born in transit, didn't choose. Their grandchildren will have no memory of Earth at all. The ship is not their vehicle. It is their world. The only world they've ever known. For them, the mission is not a journey. It is existence itself. Maintaining the knowledge, discipline, and social cohesion necessary to operate a complex spacecraft across generations of people who never asked to be there and who have no personal connection to the destination is a problem that no human institution has ever solved, because no human institution has ever had to. Every one of these challenges, food, medicine, repair, genetics, psychology, is a problem that Earth solves through scale and diversity. Earth has billions of people, millions of specialists, vast ecosystems, global supply chains, and the accumulated infrastructure of thousands of years of civilization. A generation ship must replicate the essential functions of all of that inside a container, and it must do so with zero margin for the kind of catastrophic failure that Earth absorbs routinely through redundancy and geographic distribution. A crop blight on Earth affects one region while others continue producing. A crop blight on a generation ship affects the only farm in existence. The engineering is conceivable, difficult beyond anything humanity has ever attempted, but not in violation of any physical law. The question that engineers and mission designers return to again and again is not whether a generation ship can be built. It is whether a society can be sustained inside one. The ship is a technical challenge, the civilization is a human one. And the history of human civilizations does not offer encouraging precedent for stability across millennia. But the generation ship, however distant it remains from current capability, serves an essential function in understanding why space gets more terrifying with distance. It makes visible the final transformation that distance imposes. Near Earth, the mission depends on Earth. At the moon, the mission leans on Earth. At Mars, the mission reaches toward Earth but cannot always grasp it. In the outer solar system, the mission remembers Earth. At interstellar distances, the mission replaces Earth. The spacecraft does not carry a crew on behalf of a planet. The spacecraft becomes the planet. Every function, every resource, every expertise, every social structure that once flowed from the ground to the spacecraft must now exist inside the hull, or it does not exist at all. This is the deepest meaning of what distance does. It does not change the physics of failure. A seal can crack at any distance from Earth. A fire can start at any distance. A bone can break. A pump can seize. A mind can fracture under stress. The emergencies are the same everywhere. What changes, the only variable that changes, is whether help exists. 250 miles up, help arrives in hours. 240,000 miles away, help arrives in days. 60 million miles away, help arrives in minutes as a message, but never as a hand. 500 million miles away, help arrives in hours as a message, too late for any crisis that kills in minutes. 15 billion miles away, help arrives tomorrow, for a problem that happened yesterday. 25 trillion miles away, help arrives in 4 years, for a crew that may not still be alive to receive it. The pattern is not complicated. Distance does not add new dangers. It subtracts responses. Every mile outward from Earth removes one more option, one more backup, one more person who could intervene, one more part that could be shipped, one more instruction that could arrive in time. The universe does not become more hostile. It is exactly as hostile at 250 miles as it is at 25 trillion. The vacuum is the same, the radiation is the same, the cold is the same, the fragility of the human body is the same. What vanishes is the infrastructure of rescue, the web of people and systems and supply chains and expertise and communication that turns a survivable emergency into a survived one. This is what the word terrifying means in this context. Not the terror of a sudden explosion or a violent decompression or a dramatic systems failure. Those are acute events. They are frightening, but they are finite. The terror of distance is chronic. It is the slow, steady realization that every layer of protection is peeling away, not because someone removed it, but because the spacecraft moved past its reach. Each layer held as long as it could. Voice held until the delay outran the emergency. Rescue held until the distance outran the vehicle. Resupply held until the transit time outran the shelf life. Expertise held until the lag outran the diagnosis. Each one stretched as far as physics allowed, and then it let go. Not with a snap, but with a slow, silent release, like a hand losing its grip on a rope one finger at a time. There was a threshold somewhere in this gradient, and it is not marked by any sign or boundary or beacon. It is the point at which the crew of a spacecraft realizes, not as an abstract fact, but as a felt understanding, that Earth cannot help them anymore. The planet still exists. They may still be able to see its light, a faint point among billions of others, indistinguishable from any other star without a chart. They may still be able to calculate its position, predict its seasons, estimate what time it is in Houston. They may still be able to compose a message and transmit it, knowing that someone, years from now, will hear their voice. But the connection that once sustained them, the real-time, immediate, life-saving connection between a crew in danger and a planet that could respond, has dissolved. It dissolved gradually over millions of miles, one thread at a time, and now it is gone. That moment is not the moment the spacecraft passes a specific distance marker. It is not determined by miles or light years or signal delay in seconds. It is determined by the moment a human being inside that vessel understands, with the clarity that only lived experience provides, that no one is coming. That the voice from Houston, if it arrives at all, will describe a solution to a problem that was solved or fatal long before the words left Earth. That the medication on the shelf is the last medication there will ever be. That the air recycler must be repaired by the hands in this room, or it will not be repaired. That every member of this crew is the last specialist, the last surgeon, the last engineer, the last psychologist, the last friend available to every other member, and if one of them is lost, that expertise is gone from the mission permanently, irreplaceably, without appeal. That understanding is the true destination of this story. Not a planet, not a star, not a coordinate in space. The destination is the moment when distance has taken everything it can take, and left only the people inside the vessel and the question of whether they are enough. Because space did not do this to them. Space is the same everywhere. The same vacuum. The same cold. The same indifference. Space didn't become more dangerous as they traveled. Earth became more distant, and everything they thought they carried with them. The knowledge that someone was watching. The comfort that help was available. The assurance that a mistake could be corrected from the outside turned out to be a function of proximity, not of capability. The expertise still exists on Earth. The hospitals still exist. The factories, the supply chains, the millions of engineers and scientists and doctors who could save them, they all still exist. They are all still there, on that pale point of light receding behind the spacecraft, fully operational, fully staffed, fully capable of solving any problem the crew faces. And none of it matters, because the distance has made it all unreachable, not gone, unreachable. The cruelest form of loss, the kind where the thing you need still exists, but cannot get to you in time. This is why space gets more terrifying the farther you travel. Not because the universe changes, because the relationship between the traveler and the only source of help in their entire existence changes. Every mile is a subtraction. Every hour of signal delay is a widening gap between a question and an answer. Every month of transit is another month during which anything that breaks must be fixed by the people who are already exhausted, already isolated, already carrying the weight of knowing that the safety margin is thinner than it was yesterday and will be thinner still tomorrow. The universe offers no opinion on any of this. It does not care whether humans explore or stay home. It does not punish ambition or reward caution. It simply enforces its geometry. Light travels at one speed, distances are what they are, and help, no matter how willing, no matter how brilliant, no matter how desperately offered, cannot outrun the speed of light. So the crew of any vessel, at any distance past the point where the last thread has snapped, faces the oldest and simplest version of the human condition. The version that existed before cities, before language, before fire. The version where survival depends entirely on what you know, what you carry, and who is beside you. The version where no one is coming. Where the storm must be weathered with the tools already in your hands. Where the injury must be treated by the person next to you or not treated at all. Where the decision you make in the next 60 seconds will determine whether you see the next morning. and no authority on Earth can review it, approve it, or correct it in time. That version of existence is not theoretical. It is the lived reality of any human being who travels far enough from Earth. And the terrifying part is not arriving at it. The terrifying part is watching it approach, feeling the threads loosen one by one across millions of miles, hearing the delay creep into every conversation with home, watching Earth shrink from a world to a disk, to a dot, to a point, to nothing, and understanding, gradually irreversibly, that the silence surrounding the spacecraft is not the absence of sound, it is the absence of help. The universe is full of noise. Stars burn, radiation hums across every frequency. Cosmic dust whispers against the hull. The spacecraft itself creaks and sighs and vibrates with the mechanical breath of its own systems. There is no silence in space, not really. The silence is between the crew and the only planet that knows their names. And that silence, the silence of distance, the silence of light years, the silence of a message that arrives too late, grows 1 mile deeper with every mile they travel. It does not announce itself. It does not arrive with an alarm. It settles in the way night settles, so gradually that you cannot say exactly when it began. Only that when you look up, the stars are out, and the place you called home is among them, bright enough to see, too far to reach. A light that still travels toward you, faithful and exact, carrying warmth that left its source years ago, reaching you now and unable to save you from anything.